Hello and welcome back. In today's session, we are going to discuss about complexity analysis. It is one of the main topics within algorithms and data structures, mainly because it helps in identifying the efficiency of your algorithm. And also, if your problem has multiple solutions, it helps in identifying the best one by using efficiency as a factor. So the efficiency of the algorithm can be determined by using two factors, that is time and space. So time complexity is nothing but the time taken to execute your algorithm for a given input. And similarly, space complexity is the space required to execute your algorithm for a given input. So let's take a simple example and see how we will calculate the time and space complexity. So I'm writing a simple pseudocode for finding the sum of n elements. I'm going to initiate sum as 0, and for a in numbers, I'm going to do sum plus equal to a, and the numbers would look like something like this. So let's say there are some random 5 numbers for now. And if I run this program in my computer, then it might take some 1 or 2 seconds. Similarly, if you run this in your machine, the time taken might vary depending on various factors like the CPU or the processing capacity. So it is not a standard mechanism to represent the time by using either seconds or microseconds. Instead, we need a better way to represent the time taken to execute this particular piece of algorithm. And similarly, for space complexity, right now this algorithm doesn't take any extra space while executing the algorithm. Say now I add another list here which keeps track of the running sum. I'm going to just call it as running sum, and I'm going to just add the first element here by default. And every time the loop runs, I'm going to append the current sum into this list. Because this space didn't exist while starting to execute the algorithm, whereas we created this during runtime to store some additional values as part of our algorithm. So this accounts to our space complexity. But again, similar to time complexity, representing the space complexity as bytes, bits, or gigabytes is not possible because it will vary depending on your data type. So imagine if you're storing numbers in this list as we did now, then the space complexity will differ if we are representing it by using bytes. Whereas if you used strings, then it will be more than numbers, right? So each data type will be different. In that case, it's better to have a standard representation to calculate the space complexity instead of using the specific measurements like bytes or bits. However, in both the cases, you would have noticed a similarity. That is, the space required as well as the time required will increase based on the number of elements in your list. So, say the number of elements in the numbers list is 10 now, then the time complexity will definitely increase because the time taken to execute this function totally depends on the number of elements in the array, as we are iterating through the numbers exactly once. So if the number of elements is 10, the time taken would increase. Similarly, even the space taken would increase because the length of the running sum list will increase based on the number of elements in your given list. So what this tells us is that we need some representation on the basis of the number of elements which we have in the given list. So that is where big O notation comes into picture. Big O notation is nothing but representing the time taken or the space required to execute your algorithm depending on the number of elements given as an input. So if we would want to represent time and space complexity of this particular algorithm in big O notation, then it would look something like big O of n, because the space required and the time required both increases based on n linearly. So as n increases, the space required also increases, where and also the time required increases. Okay, I have cleared out the board and written some of the famous big O notations in their increasing order of complexities, starting with big O of 1 till big O of n factorial. So let's start with big O of 1. This is also called as constant time because as n increases, the time taken to execute the expression doesn't increase. The best example for this is a simple arithmetic equation which doesn't depend on n. So in this case, I have just written x equal to a plus b. So if n is 1, 10 or 1000, still the time taken to execute this particular statement will be the same. So that is why we call it as constant time, because as n increases, the time taken to execute the statement still remains the same. So moving on to log n. So to understand log n, first we need to understand the logarithmic equation, which is log a to the base b is equal to y if and only if b to the power y is equal to a. So in our case, this becomes log n to the base 2, because if we don't specify any base, then by default it is 2, is equal to y if and only if 2 to the power y is equal to n. So if you see, as n increases with huge amounts, still y will increase only by a little factor. Let's see why. Let's take some n values as examples. So let's say 2 to the power 1 is 2, 2 to the power 2 is 4, then 8, and 16, 32, and so on. Whereas in all these cases, y will still be 1, 2, 3, and so on, right? So as n tends to infinity, y will still be increasing only by a little factor. So that is why we call log n as even more efficient than n itself. And the best example for log n is binary search. We will see that in a separate video along with its workings. So moving on to O of n. The best example for O of n is a single for loop. And the example which we saw in the beginning of this session applies very well to this, that is finding the sum of n elements. So we are iterating through the elements just once. So as n increases, the time taken also increases by the same factor. And n log n, everything which we discussed about log n applies for n log n as well. Just that we are multiplying log n with n. So the number of operations taken to execute the algorithm in this case would be n multiplied by log n. And the best example for this is merge sort. Again, we will see that in a separate video. Moving on to n square. The best example for n square is double for loop. So if we have for I in numbers and for j in numbers, this means we are iterating through the entire list for every element in the list. So this particular statement takes O of n time, and again this statement takes O of n. So since this statement is within the first statement, we can write this as n multiplied by n, which leads to n square. And imagine if we have another level of for loop here, so for k in numbers, then this will lead to O of n cube time complexity, because this results in n multiplied by itself 3 times. And next, let's see about 2 to the power n. So the best example for 2 to the power n is finding all the subsets for a given set. So let's take the given set as 1 and 2, that is 2 elements in a given set. Then 2 to the power n is 4. So because the subsets for this particular set is 1, 2, and the set itself, and then an empty set. So as you can see, n is 2. Finding the number of subsets for such a set is 2 to the power n, which is 2 to the power 2 and 4. So this is 2 to the power n. And finally, n factorial is nothing but n into n minus 1 into n minus 2, so on, up to 2 into 1. So as n increases by a very small amount, n factorial increases vastly. This is not an ideal time complexity. So it's always advised to stick with the initial few time complexities. And the best example for n factorial is traveling salesman problem. And we'll see that in a separate video. All these that we discussed for time complexities applies for space complexity as well. I have made some space again. Now let's quickly write out some values considering n as 5 and n as 10 and see how these values drastically change. And when n is 5, in case of O of 1 time complexity, the time taken actually doesn't change. So this will still remain as 1. And when n is 5, log n would be approximately equal to 2 because 2 to the power 2 is 4. So let's say it's approximately equal to 2. Then O of n would still be 5. And n log n would be 5 into 2, which is 10. N squared is 5 squared, which is 25. And 2 to the power n is 32. And n factorial in this case will be 5 into 4 into 3, 2 into 1, which is 120. And in case of 10, say n has increased only by 5 units, then the number of operations required will stay the same in case of O of n because it doesn't depend on n. And in case of log n, it will increase only slightly, that is 3 because 2 to the power 3 is 8. So let's approximate it to 3. And O of n in this case would be 10. And n log n would be 30. And n squared is 10 squared, which is 100. And 2 to the power n will be a drastic change, which is 1024. And n factorial is out of the charts now because it's approximately equal to 3 million. I had to use calculator for this one. So this is why we call n factorial as not an ideal time complexity or space complexity, because as n increases by a very small amount, the number of operations which are required to execute your algorithm or the space taken would increase by a very huge amount. So before ending the session, I want to call out about one last thing, which is worst case analysis. Pico notation is always called as the worst case analysis because imagine you have two set of statements in your given algorithm, and the first set of statements actually runs a merge sort to sort your elements in the algorithm, and followed by which we are running a search on the algorithm to find a specific element. In that case, if you see, this particular section will take n log n, and whereas the binary search will take log n. So we would call out the combined time complexity as log n plus n log n. However, in case of Biko notation, we would take only the worst case. That is, when compared to log n and n log n is obviously higher than log n because it is multiplied by n. So we can drop out this log n value and just say that our time complexity for this algorithm is log n. So this is what we call as worst case representation. If there are two different sections of code in our algorithm and each section has its own time complexity or space complexity, then we pick the worst case time required to execute our algorithm and call it as the time complexity of our algorithm. And this applies to space complexity as well. So if there are two sections in your algorithm and each requires a different amount of space to execute our algorithm, then we pick the worst space complexity as the entire space complexity of our algorithm. But notice that if you have two different sets of inputs, say you have two different lists which has n elements and m elements, and these are given to your algorithm, and there are statements within your algorithm which takes O of n time and O of m time, then in this case you can't combine O of n and O of m into a single time complexity because these are different parameters and we don't know which list has the higher number of elements. So we have to still write it as O of n plus O of m. And the same applies to space complexity as well. Hope this all makes sense. It's a lot to take in, but it'll all come together when we start looking at problems and finding out the space and time complexity for each of the problem. And if you have any questions, please leave them in the comments below. See you soon in the next video. Thank you.